Hello, Chem 30, and welcome to your lesson on pH and pOH and the scale and solving for it. Basically, everything pH and pOH you're going to find right here, today, right now. So the pH scale, the whole purpose of it is essentially just to show acidity or basicity, kind of indirectly, of a solution in an easy to show way, right? A number that's a lot easier to show or use than a hydronium or a hydroxide concentration, because hydronium and hydroxide concentrations are incredibly ugly with their negative exponents. I'm sorry, it's offensive, but they're ugly. So instead what we're going to do is we're going to use these simple numbers for pH and pOH that represent it as a number that isn't with exponents, just a simple number with decimal values. So that's the purpose of pH. There's kind of a whole thing about power of hydrogen for pH. From my understanding, that's actually just kind of not, you can think of it that way, but that's not what it was meant to be. P is just kind of like this kind of unknown notation in chemistry that's used a lot. So yeah, it's just, that's somewhat meaningless that the letters are what they are. But anyways, it is important to know that for the pH scale, every step I take on the pH scale is a 10 times difference in acidity or basicity. So for example, if I have a tomato with a pH of 4 or a potato with a pH of 6, how much more acidic, if this is truly the number for tomatoes and potatoes, is a tomato than a potato? And the answer is that it's 100 times more acidic, because it's 10 times from 6 to 5, and then another 10 times from 5 to 4. So the difference in acidity is 10 to the power of 2, or 100. And the same way, let's get crazy, how much more acidic is lemons than bananas? 2 as opposed to 5. And the answer would be 1,000 times. 10 times 10 times 10. So kind of interesting, but that's a pH scale. Let's talk about how to calculate pH, and this should be a review. You learned about this in Chemistry 20, and of course we have this shiny log here because it is all about taking logs. You might now understand logs better after learning about it in math, but what logs are is if I have something like, let's say, 1,000 is equal to 10 to the power of x. Well, if I take the log of 1,000, it's going to tell me, hey, that exponent is 3. So it's solving for the exponent for a base, which it's normally 10 with a normal log function, it's just 10. So what exponent as a power of 10 will get me the number that's in the brackets of the log function? Okay, so if I were to write this out, log of 1,000, writing, is equal to 3, right? So that is solved for this. If I want to find pH, pH is simply equal to the negative log of the hydronium concentration, H3O positive concentration. So if I type in negative log hydronium, I will get as a result my pH value. Now the sig digs for pH values are very interesting in that for pH values, only the decimal places count for sig digs. Okay, so only decimal places count for sig digs. And this is only for the pH or later on the pOH values. This doesn't apply to concentrations, right? It applies for pH and pOH. So for example, if I have a pH equal to 3.71, and I ask you how many sig digs this has, well, it has 2 sig digs because it has 2 decimal places. Now, what about something like 11.024? That would have 3 sig digs because it has 3 decimal places. So when I count sig digs for pH or pOH, only the decimal places count. The numbers before the decimal point do not count in sig digs. All right, so let's get into a calculation and see if we can find pH. So a neutral solution at 25 degrees Celsius has a hydronium concentration of 1.0 times 10 to the negative 7 moles per liter. What is the pH? Well, pH is equal to negative log of hydronium, H3O positive. So I have negative log of 1.0 times 10 to the negative 7, right, moles per liter. I'm putting the units in there. You probably don't have to in a pH function. pHs are unitless when I calculate it out, so nothing's really happening in the unit for this. So when I go ahead and plug this in, and I already know what the answer is. The answer is 7, by the way, because of the nature of how logs work. But what I would do is I would press negative, right? So down here, not minus, but negative, log, and then 1.0, second e, that comma e thing, the exponent again, negative 7. And that's going to get for me the answer of 7 for the pH. Now I got to be careful with sig digs here, right? Because it was, and I kind of messed up because it's 1 here and I wrote 1.0, so it's just 1 times 10 to the negative 7. This had 1 sig dig, so now I need 1 significant digit for my pH, which means it would be 7.0, right? I have 1 sig dig, 1 decimal place, okay, because I had 1 sig dig in my concentration. So again, for concentration, sig digs are how they've always been. We just count the numbers, right? We count how many numbers we have. And yeah, trailing zeros we don't, or leading zeros, sorry, we don't count. Trailing zeros we do. But when I talk about sig digs, only the decimal places are counted for sig digs. So I have 1 sig dig here. All right, that was that question. Let's go to pOH now. pOH, Winnie the Pooh, it's almost the same word. All right, so pOH formula, this is pretty much the pH formula, but it's for hydroxide instead of for hydronium. So pOH is equal to negative log of OH minus, right? So same thing. This is pOH is just like pOH, but it's hydroxide instead of hydronium that it's tracking, and this is my formula. So now let's try to use this. No, let's not. Let's instead talk about pH and pOH and how they correspond. Really important to understand how the relationship is between pH and pOH. And in fact, on assignments and stuff, and if you had tests, I would tell you to do this on tests, I would actually make this kind of line scale thing comparing pH and pOH. So if this is acids on this side, and this is bases on this side, right? And let's say this is like 0 for pH, and this is 14 for pH, and this is 7. Then if I look to the pOH scale, it meets up at 7. Neutral is neutral, so 7 for pH is equal to 7 for pOH. Now as I track pOH, as it gets more and more acidic, it actually goes up in number, right? As it gets more basic, or acidic, sorry. And then as I go to more basic, it goes down in number towards 0. So this is how it matches up. So this would be something that's interesting to actually draw again on assignments or tests to keep track of what's going on. Now, wording is tough with this. If I say the pH increases, that means it's getting more basic because I'm talking about pH as a number. A lot of people, when they hear the pH increases, they think pH is synonymous with acidity. It's not. pH measures acidity. But when I talk about pH, I'm talking about pH as a number. So high pH means it's getting more basic. If I lower the pH, it's getting more acidic. So really important to understand that terminology and how that works. pOH, if I'm increasing pOH, I'm making it more acidic. If I'm lowering pOH, the solution is becoming more basic. All right, so that's what I already talked about. Confusing, yes, but remember the terminology of increasing, decreasing, that pH and pOH is a number. So think about it in terms of its number properties. Look at this scale that you draw for yourself, and then you can make sense of terminology like raising or lowering pH or pOH. Makes it a lot easier. All right, so how does pH and pOH relate? Well, if you didn't already figure it out from, I know I'm skipping around slides a lot. If you didn't already figure it out from this, what does pH and pOH always equal? The answer is 14. pH plus pOH will be equal to 14. So we can actually use this as a law to change between pHs and pOHs. It's a nice, easy formula. So a neutral, I mean, pretty obvious, right? But 7 plus 7 equals 14. A reminder that I can have pHs and pOHs that are negatives, right? So the scale of 0 to 14, it can be outside of that scale. So for example, sulfuric acid, if I have concentrated sulfuric acid, it's got a pH that's actually lower than -1. It's between -1 and -2. Okay, so if I have a pH of, let's just throw it out here, pH of -1.4, okay, then that means that in order to get 14, my pOH would have to be 15.4. Okay, so I can have pHs and pOHs that are negative, but it always is going to add up to 14. So I have another law here to get between all this stuff. So now I've learned a law for calculating pH, for calculating pOH, and then also that relates pH and pOH. Now we have to talk about the reverse. We also can convert between pH, pOH, and hydronium and hydroxide. For hydronium, how we do that, H3O positive concentration is equal to 10 to the negative pH. Well, for hydroxide, OH minus, I have 10 to the negative pOH. This should be a review, but these are my formulas for finding hydronium or hydroxide. So how does that plug into your calculator? Well, what you do is you actually go second log, okay, like that, and then you have 10 to the power of, and then you can enter in, let's say, negative, let's say the pH was 2.5, negative 2.5. So if I had a pH of 2.5, then my hydronium concentration, H3O positive, would be equal to, now I only have 1 sig dig from this pH, how I wrote it, right? It would be equal to, let's say, 0.003 moles per liter. Or I could write this as 3 times 10 to the negative 3 moles per liter. So that's a quick example of a conversion, right? Nothing fancy there, but quick example of a conversion between pH, pOH, hydronium, or hydroxide. So now we bring it all together. This graphic, huge, super important. I can use pH, pOH, hydronium, or hydroxide, and I know this is H positive, but just treat this as instead hydronium, to convert between one thing to another thing to another thing. So if I have any one of these pieces of information, I can find all of the other three because I can work through this square and the formulas in order to find the other stuff. So if I have a hydronium concentration, I can find pH, then I can find pOH, then I can find hydroxide, right? So sometimes you'll have questions where it's like, hey, here's the concentration of hydronium, what's the pOH? And you can do that by going from hydronium to pH, and then from pH to pOH. Or if you wanted to, you could go from hydronium to hydroxide, and then hydroxide to pOH. It's user's choice, right? You can figure it out whatever way you want to, but these are all of the relationships that we have between these four different quantities. It's four different variables, okay? So any solution, right, that has water as a solvent, I can go through this in order to find concentrations of hydronium, hydroxide, pH, or pOH. And the reason why this works is, again, because of that self-ionization equilibrium of two water molecules reacting to make hydronium and hydroxide. So let's give it a go. Communicate a hydrogen or hydronium, right, equivalent. One is Arrhenius, one is modified Arrhenius theory. Ion concentration of 4.7 times 10 to the negative 11 moles per liter as a pH value and a pOH value. I can do that. So let's get into it. Let's calculate pH first. pH is equal to negative log of hydronium, H3O positive. So I have negative log of 4.7 times 10 to the negative 11 moles per liter. And I'm going to work that out to figure out what my pH is. Let's go to my nifty calculator here. Negative log 4.7 second E negative 11. Plug that in, close those brackets, press enter, and I get this answer for a pH. Sig digs. Now I had 2 sig digs for my concentration, so I need to have 2 decimal places on my pH value. So that's going to give me an answer of 10.33. Okay, so now I got to find pOH. Well, I know that pH plus pOH is equal to 14. Going to treat that as an exact number. Okay, so 14. So now what we can do is just say, well, what is pOH? Well, pOH would be equal to 14 minus pH then. So I have 14 minus 10.33, and I end up with 3.67 as an answer for that. So that would be my pOH value then is 3.67 at the end of the day. Yeah. Don't like how I wrote that, so I'm writing it again. pOH equals 3.67. Now I do the rectangle. Beautiful. All right, so that's that question. That's that example. Let's see if you can do this one. So this would be an example that you can try out, see how it goes. Before you get into it, though, just remember that if I have 0.500 moles per liter of hydrochloric acid, then that means that because all of the HCl aqueous reacts with water to make hydronium and chloride ion, and this is quantitative because it's a strong acid, it all reacts, that as a result, I have a concentration of hydronium, H3O positive, of 0.500 moles per liter. So I've got my hydronium concentration. So now can you figure out the hydroxide ion concentration? And here's a solution. Kw is equal to hydronium multiplied by hydroxide, OH minus. So I'm solving for hydroxide. So I have OH minus is equal to Kw divided by hydronium, H3O positive. So I have 1.0 times 10 to the negative 14 divided by 0.500. And if I plug that into my calculator, boop, 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 I'm multiplying by 2 because I'm dividing by 0.5. That's going to give me a hydroxide concentration of 2.0 times 10 to the negative 14 moles per liter. So that will be my hydroxide concentration for this. You might think, oh, that's really low. Is that right? Well, remember, this is a strong acid and it's quite a high concentration. So my hydroxide is going to be very low. It's going to be tiny. And if I multiply this by this, it will get me that 1.0 times 10 to the negative 14. So that's the answer to example number 2. This is getting into the next level. Calculate the pH and pOH of a solution prepared by dissolving 200 grams of lithium hydroxide in enough water to make 4 liters of solution. Honestly, this might be a little bit tough, so I'm going to walk you through half of it because I think it's important for you to see a concentration of ions type question for this, and then you're going to do the second half. So lithium hydroxide, how is it going to make, well, I'll tell you, a base in water? It's going to dissociate. So I have LiOH aqueous dissociates to make Li positive aqueous and hydroxide. Everything that's group 1 ions is soluble in water, so all of it will dissociate in order to make these 2 ions. So I have 200 grams of this, right? I want to figure out how much hydroxide I'm getting. So first of all, let's figure out my moles of lithium hydroxide. Moles of LiOH is equal to mass divided by my molar mass. So I have 200 grams of lithium hydroxide. Quick molar mass calculation. Lithium is 6.94 grams per mole, right? O is 16.00 grams per mole. And then my hydrogen is 1.01 grams per mole. So if I add all that together, it would be 23.95 grams per mole. So I have 200 grams divided by 23.95 grams per mole to figure out the moles. So let's go ahead and just plug that in. 200 divided by 23.95. And I end up with an answer of 8.35 moles. Now that is not yet where I want to be. I want to now say that concentration of LiOH is equal to N over V, right? Moles divided by volume. So I have 8.35 moles divided by the 4.00 liters I have of solution. So I'll go ahead and take this and divide it by 4 and end up with 2.09 moles per liter. And now that I've got that concentration, I can now relate this to hydroxide. So OH minus is equal to 2.09 moles per liter of LiOH aqueous multiplied by 1 hydroxide, OH minus, over the 1 lithium hydroxide that I have going in. So all I'm doing here is just proving that my lithium hydroxide concentration is the same as my hydroxide. Every lithium hydroxide I put in turns into hydroxide when it dissociates in water. So I end up with the same concentration of 2.09 moles per liter for my hydroxide concentration that I have going into this. All right, so that's the point now where we're dealing with this new acid and base work. What we did so far, that was actually just Chem 20 concentration of ions work. Now we're into the new stuff of finding from this pOH and pH from that. I'm going to do some work over here. Okay, so I'm just going to kind of erase this so I can do my work over here for pOH. So pOH is equal to negative log of my hydroxide concentration, OH minus. So I have negative log of 2.09 moles per liter. And now I can figure out from that my pOH, sorry. So let's plug that into the calculator here. I have negative log of 2.09, and that equals negative 0.320. I have 3 decimal places because I'm dealing with 3 sig digs in this question. So 0.320 is my answer for pOH. So then if I'm going to find pH, that will be equal to 14 minus my pOH. So I have 14 minus negative 0.320, and that's going to give me a pH of 14.320. So those are my final answers. I have a pOH of negative 0.320 and a pH of 14.320. As soon as you get to a concentration higher than 1, it's going to end up with a pH or a pOH that's negative, right? So that's just kind of a given. Now, one of the concentrations is 1 or over. I should say over 1, not 1, but over 1, then as a result, pH or pOH, one of the two is going to be a negative value. So don't be alarmed by those negatives. All right, that gives you some examples. That's it. Really big thing is understanding this beautiful, beautiful square. How to go from hydronium to hydroxide to pOH to pH, getting all in between those different kinds of variables and values. That's critical. That's the skill you're learning here. A lot of it you already knew. You knew this formula, you knew this formula, this and this from Chem 20. We just added those crossbars, pH plus pOH equals 14, and our KW expression from the other day. So we can now convert from one thing to all of the other things. All right, that's it. Have a good rest of your day.